all of you for joining and welcome again. And let me now start by sharing my slides. I hope the slides are now visible.
Yeah, it's visible.
So we start exactly at 12 p.m. and we would try to wind up by 1:30, so 1.5 hours. So let's get started. Okay. So the title of my talk today is will be focused on machine learning and computer vision for big data processing to address some of the global challenges. Okay, and in the last part of my talk, I have used some amount of high performance computing. So I would be happy to share some results with you. So I would start with a very basic introduction to machine learning, and then gradually move towards some of the work that I have done and would like to share with you. So I work in the area of data mining, data science, and also popularly known as data analytics and applied machine learning. And I use data mining and machine learning especially to handle big spatial data. My interest also lies in spatial computing and spatial databases. In the institute, I teach GIS and spatial computing and databases and machine learning. And since most of the work involves images, so therefore a lot of image processing techniques are also used here in the research. So I promote and use free and open source softwares, and definitely use it for many applications from statistical analysis to GIS, landscape, databases, Linux, probably in all possible domain. So for today's talk, I would start with a small overview on machine learning. Perhaps many of you may already be aware, but keep it as a preliminary material just to introduce to the audience who may not be completely into machine learning topics. And then I would subsequently go into few examples, trying to show you with some case studies, and then I will try to spend some time on one of the topics that is very popular right now, called subpixel learning, subpixel classification problem. Later on, at the end of the talk, I would like to present you some of the challenges and opportunities in the geospatial domain while using machine learning techniques. So I would like to start with something very interesting. Probably all of us are currently of the view that computer science is among the most sought after courses right now. But you will be surprised to know, and believe me, that not computer science, but statistics is a field that is continuously being challenged by science and industry problems. Okay, so we have already seen that data has been growing multitude, and then there is a lot of improvement in hardware and softwares. Probably the hardwares have not become cheaper, and then because of the limitation of humans in analyzing the huge data sets, the growing volume of data sets, people have now moved to using automated ways of computing, using the low-cost hardwares and different computing resources available. So statistical problems have actually grown a lot in both complexity and also in volume. When I say volume, it is mostly referring to the size of the problem. Okay, and the essential challenges in handling such huge data sets are how do you store that data set, how do you manage that data set, how do you organize that data set, and then once you have done some of these pre-processings, how do you perform certain search or certain look at certain patterns that are not very trivial. Okay, so all these related issues of storage, organization, searching, trying to look at some pattern, I would say non-trivial pattern. They led to the new field of data science, which is perhaps now in the current market most sought after and most demanding. Because of the huge data set, huge volume, a lot of people are now trying to move into the data science domain. So what is the challenge? What is the challenge in the entire domain? The challenge is that once you have stored, organized the data set, okay, what do you do with the data? So the one important thing that we can possibly do with the data is to extract some of the important patterns and trends from the data. So these trends, these patterns are not very trivial, and you may not be able to discover them or find them, visualize them just by looking at the data because of the volume. So what we try to do is we try to see what patterns and trends can be found out using some of these data science techniques. Data science techniques. So slowly we will move towards machine learning. Okay. And since we are using these data sets, the large data sets, the big data sets, okay. In a nutshell, we say that we are trying to learn something from the data. Whatever patterns, whatever trends we try to discover from the data, essentially it all depends on the data. So therefore, in a nutshell, we can say that we are learning from the data to improve our knowledge, to improve our information, and ultimately to have a nice decision based on the data. So we can say that we are trying to move towards a data-driven decision. Okay. Now coming to the topic machine learning. Machine learning is a smaller topic compared to data science, where machine learning only focuses on more of computing. Okay, whereas data science is a probably a larger domain, which also entails data collection, data cleaning, data pre-processing, making data cubes, and so on. Right. Even once you have generated some results, even the way you present your results, the way you draw charts, figures, graphs, etc., are all part of data science. Whereas machine learning are essentially some kind of computer programs, okay, that help us to automatically improve with learning and with experience. So the more and more data we provide, more and more your computer program will try to learn from those data sets and improve based on the newly added data sets. Okay, so a good way to understand machine learning problems is to view this machine learning as view this machine learning from different perspectives. Okay, from different perspectives. So you can try to understand the problem setting, algorithms, assumptions that that underlie beneath each of these techniques. Okay, so the key point here is that we try to look ML from many perspectives, but not rather thinking just from the algorithmic perspective, but also as a user, as a stakeholder. How do you view the problem, and then how do you understand the problem, and then comes the role of machine learning expert. We look into the settings, algorithms, assumptions, etc., and so on. So here I would like to point out something. So we have been listening to the word machine learning quite a few number of times. Until recently, um, Robert Shirani, who is a professor of biomedical data science at Stanford University and statistics, happens to be one of the highly cited researcher in machine learning. As per the Google Scholar, he has more than 165,000 citations in the field of machine learning. Okay, so I have a quote from his website. So I happened to visit his website, and I was going through the kind of work he is doing. And then I just looked at two paragraphs. Okay, so I have copy pasted the same paragraphs here from this particular website, and I would read it for you. Okay, so there is something interesting hidden in these two paragraphs. Okay, and I would then point out what is that something interesting, right? So he writes on his website, on his official website, that in elementary and high school, I loved mathematics. As an undergraduate in university science courses, I found that math got to be too abstract for my liking. Computer science seemed seemed concerned with little details, like, for example, trying to save a microsecond or a kilobyte in computation. In statistics, I found a subject that combined the beauty of both math and computer science, using them to solve real world problems. Okay, then paragraph change. Today's statistics is more important than ever because of the ease with which we can collect large amounts of data. The challenge is to sort through all of this data and separate out the consistent patterns from the noise. Okay, consistent patterns from the noise. This challenge now touches many areas of science, engineering, medicine, finance, and even the arts. Statistics is a young subject still finding its way. It is an exciting time to be a statistician because of the enormous computational tools at our disposal. How best to use these tools is a fundamental challenge for our subject and the focus of my research. Okay, so what is that something interesting if you have observed in the two paragraphs? Okay, remember that I started this discussion by showing his picture, and I told that he is currently one of the highly cited researcher in machine learning in the world. Okay, now reading at these two paragraphs, what is something interesting that you might have observed? Okay. So because of the time constraint, we will not take feedback from each of you, but let me reveal that. Okay. The important point to see here is that there is no mention of machine learning in these two paragraphs. Okay. And now this person who is a statistician happens to be one of the greatest researchers in machine learning at this point of time in the world. Right. It means that machine learning doesn't always belong to computer science domain, but people from different domain, biostatistics, statistics, mathematics, earth sciences, and so on, can become expert and use machine learning techniques in their day-to-day research. Okay, so it takes a while to become familiar with the machine learning algorithms, techniques, etc. But the domain is not restricted to only the people who belong to computer science, but is rather open to everyone, from all disciplines, and it depends on individuals how far they can explore, how far they can use all these techniques to handle their day-to-day research. Okay, so a brief history about machine learning. Okay, so machine learning basically earlier was popularly called statistical learning. Okay, and it began at the beginning of 19th century when Legendary and Gauss published their first paper on least squares. Okay, and probably this least square it implemented the earliest form of linear regression. At that point of time, it was used in astronomy. Okay. Later in 1936, Fisher proposed the linear discriminant analysis. In 1940, logistic regression came. Then in 1970, Nelden and Wedderburn they coined the generalized linear models. Many of you might be already using these models. 1980s, non-linear models came into picture. Mid 80s, Bremen et al. Introduced CART. So you might have already seen, studied or used CART, which is classification and regression tree. Okay, it is popularly used in classification task. 1986, the researcher I was talking about, Shasti and Tipshirani, they coined the generalized additive models. Okay, and then onwards came the term statistical learning, which became now very popular as machine learning. Okay, so what is learning? What is learning? We talk about in the entire process. Okay, so I have a few examples to make it more vivid. Okay, so let's say imagine computer learning from medical records. These treatments are most effective for new diseases. Okay, houses learning from experience to optimize energy cost. So you may have already seen some of the digital assistants like your Alexa or Google Assistant, or so these typically listen to humans and they operate. For example, switch off the light, switch on the fan, okay, make the room brighter, and so on. So these assistants, they are often programmed to also optimize the amount or quantity of energy that the house is utilizing. Okay, so that the electricity or gas consumption is reduced. Okay, or personal software assistants such as your Cortana or your Alexa or any other assistant that we use in our cell phone, in our iPads, and so on. Right. These are also softwares, okay, that learn from our day-to-day behavior. For example, the way we use these Google Assistant, the places which we visit, etc., and the way we speak, etc., are recorded by this Google Assistant, and then tries to help us by giving suggestions, by giving solutions. For example, if you visit your office every day, you start at 9 and come back at 6, right? So your Google Assistant will inform you at 8:30 what is the traffic, how much time it will take to reach the office, and so on, the weather conditions and so on. Right? So all of these, they have software programs that learn from our day-to-day behavior, our interaction, and they keep improving. Okay. So in the overall picture, the word learning here, okay, word learning here is not meant to perceive as the meaning of the English word learning. Okay, is not to analyze the meaning of English word learning. Rather, instead, the word learning here defines precisely a class of problems, okay, a class of problems, right, that encompass interesting forms of learning. Okay, for example, computer learning, medical records, house learning, how to optimize energy, personal software assistant, and so on. Okay, and then after learning to explore algorithm to solve these problems. Okay, the structure of the problem, the procedure of how to solve them, etc. Okay, so we have seen a few learning examples, but to be more specific and narrow down to some popular machine learning examples, predict whether a patient hospitalized due to heart attack will have a second heart attack or not. So these will be based on several parameters, vitals, demographic, diet of the person, clinical measurements, and so on. Okay. Second example, predict the price of a stock in 6 months from now. Okay, based on different criteria. Identify numbers in a handwritten zip code. Okay, so you have an image and you try to identify what is the numbers written in the zip code. Okay, estimate the amount of glucose in the blood of a diabetic person from infrared absorption spectrum of that person's blood. Identify the risk factors of prostate cancer based on clinical and demographic variables. Okay, so all these terms, they involve predict, identify, estimate, identify. Right? So all these terms are statistical terms such as prediction, estimation, etc. So therefore, the underlying principle of machine learning problems, they come from statistics. Okay, so this is a very rudimentary example trying to separate out two different data sets. So you have a feature one and feature two. Feature two. Okay. The two data sets in this example are easy to separate because they can. You just draw a straight line. And separate that. Okay. But looking at this particular example, we see that probably separating the plus signs from the square gray square cells is rather a bit difficult because of the way the two data sets are arranged. Right. These data sets we might succeed in separating by using some kind of a non-linear approach. Okay, which kind of data is easier to work? Obviously, this is easier to work because the data are linearly separable, but it is not always the case, and you have more of data sets in the real world which are non-linear mixtures, and therefore they are not straightforward to separate. Okay, so the basic learning premise is that we use a set of observations to uncover an underlying process. Okay, so the set of observations are called training samples. Okay, and these training samples are drawn independently of each other. All training samples, they come from the same underlying process.
Uh, Professor Uttam, there is a question from Dr. Shirisha Poluri.
Yes.
So she in return like to have question to also.
So,
Yeah, yeah,
so
Dr.
shall we take the questions at the end so that I first finish the. You may note it down, and I will take the questions at the end of the talk. Will it be okay?
Okay, maybe this one and then.
Yeah, sure. Okay.
Yeah, Dr. Suresha, please. Hello, Dr. Suresha. Hello, Dr. Suresha. Seems to be some issue.
Okay. So I will proceed.
Yeah. Go ahead.
And we'll take the questions at the end. Uh, right. So coming back to the slide now, we were trying to look at a basic learning premise, and we saw that a set of observations, they are called training samples, which are drawn independently of each other, and they come from the same underlying process. Right. We also assume that the training samples are IID, which means independent and identically distributed. Okay. So at this point, we will not go into any of the algorithms. That will be really interesting if you try to read and explore yourself. But rather try to separate these different types of machine learning techniques that are often used. So among the recent examples we saw, classification and prediction happens to be two popular ways of analyzing data. In classification, we try to predict the categorical class levels. These class levels could be discrete or nominal, such as, for example, A, B, C, D, E, 1, 2, 3, 4, 5, or colors or ID numbers, etc. So what happens in classification? We construct a model based on the training samples. Okay, and then once your model is built, we try to use it on a test data set and then try to classify the data one of the class labels that we have already seen in the training samples. In prediction, we try to develop a model. To handle continuous valued functions. Okay, so that we predict unknown or missing values. So, for example, let's say we have a rainfall data of from 2000 to 2020, and in between, let's say for example 2012, the data is missing because of some reason. Okay, so then here we can use prediction to find out what was the missing values for 2012 based on the previous and um, uh, previous and the uh, future values. So future in the sense from 2013 to 2020. So we have a 20 years data, some values missing, and we use prediction to know that unknown value. So at this point, I would like to quickly emphasize that prediction is different from forecasting. Okay, so when we listen to the news every day, we see the weather forecast. We don't see weather prediction. Okay, so forecasting is different from prediction. Predictions are based on the current and historical data sets, whereas forecasting is based on the historical data sets to know about the future. Okay, so what is the weather forecast tomorrow? Will it rain? Will it not rain? Will it be a dry day? Will it be sunny? And so on. Whereas prediction is doing more of interpolation. Okay, prediction guarantees some kind of interpolation, but not always extrapolation. Okay, therefore it is slightly different from the term forecasting, although people often they exchange the two terms and use it. Okay, so coming to the classification that we saw in the last slide, there are two types of classification. One is called supervised and the second one is called unsupervised. We have already seen what is supervised. Supervised means you have a training data, and based on the observations you develop model, and then you classify the new data to any one of the assigned labels. In unsupervised learning, as the name suggests, this is unsupervised. There is no supervision, right? So unsupervised learning is also called clustering, right? So clustering is a form of natural groupings. Okay, so for example, given a set of measurements, observations, etc., with the aim of establishing existence of classes or clusters in the data. Okay, so you have a set of measurements, observations, etc., and we use clustering to see what could be the natural data groupings within the data sets. Okay, we will see some more examples in the subsequent slide. So you might have seen this kind of a Google car or autonomous vehicles already on roads in many of the countries. These cars, they use some kind of a learning, supervised learning. So they learn from their mistakes, okay, and keep improvising them, so that at some point of time they become so efficient that they do not make any mistakes which humans might also make. Right? For example, stopping at a red signal, allowing people to cross the road, maintaining the speed limit, and so on. Okay, so this is a form of a supervised learning. This is a form of unsupervised learning. So this particular graph shows the density of Facebook account holders across the globe. Okay, so probably in this plot, 10,000 Facebook account holders have locations have been used, and then based on some kind of a grouping, the number of Facebook account holders have been shown in the graph. So you would see that most of the users belong to North America, UK, Europe, and India. There is not a single user in China because they do not use Facebook, right? So this is an example of clustering. There is no training data, but based on the demography, based on the political, I mean the political boundary of a country, the density of number of Facebook account holders have been shown. Okay, so I have been talking about cluster analysis. So what is a cluster? Cluster is essentially a kind of collection of objects which might be similar. The collection of objects will be similar to one another within the same group. Okay, and dissimilar or unrelated to the objects in other groups. So it means to say that if you have two groups, okay, the data points in group one will be similar, and data points in group two will be similar, but these two groups are dissimilar. Okay, so cluster analysis helps us to find similarities between data according to some characteristics in the data. Okay, these characteristics are often human induced. For example, you can group data based on different criteria. You can group people based on height, based on age, based on gender, and so on. Okay, there are no predefined classes, no observations, and no observations in the sense no observations for the training samples. So no learning by observations. Okay, and the procedure involves grouping the data within itself based on certain criteria such as height of people, age of people, gender of people, the first letter of their names, alphabetical names, and so on. So these are often used as a standalone tool and also as a pre-processing step in many of the data science domains, many of the data science applications. Okay. As an example, you have several news pertaining to different domain. Okay, and then um, can we use clustering? Can we use clustering to merge them? Okay, can we use clustering to merge the similar or group the similar news? Right. So based on that, this grouping is done. So the top two news are entertainment. The center one, the middle one is politics. The rest at the bottom are sports and so on. So this is an example where we have not used any training sample, but the news itself are grouped based on some keywords that might be related to any of the three different categories. Okay, what are potential applications of cluster? We use it for a large number of applications, from data reduction to hypothesis generation and testing, prediction based on groups, finding k nearest neighbor, outlier detection. These are some applications, and there are many other broader applications in pattern recognition, in spatial data analysis, in creating thematic maps in GIS, in detecting spatial clusters, for example, trying to cluster hotspots of COVID-19 infected people around the country and so on. They are used in image processing, and they are used in market research, okay, to identify potential customers for selling out certain products. They are used in document classification in World Wide Web. They are used to cluster weblog data and so on. Okay. and there are a large number of application fields in of cluster analysis in biology, in information retrieval, land use, which is a field in GIS, in marketing, in city planning, in earthquake studies, in climate change studies, in economic studies, and so on. Okay, so now at this point, I would like to show you one slide and then try to differentiate between regression, classification, and clustering. Right. So in regression, which is used for essentially for prediction, output variable to be predicted is a continuous variable. Okay, for example, rainfall of different years or of different months, average rainfall of different months, okay, or scores of students in exams. Okay, classification on the other hand, the output variable is to predict a categorical variable such as numbers, IDs, labels, ABCD, land use classes, etc., and to classify emails based on their content. Okay, for example, into professional, marketing, personal, and so on. Clustering, there is no predefined notion of level. Okay, and we try to form groups or clusters. Okay, out of these, regression and classification, they fall under supervised learning methods, whereas clustering, it falls under unsupervised learning method, where you do not have any or supervision uh, 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 supervision of any training data learned. Okay, so summarize, in supervised learning, you have regression, classification, both have labels. In unsupervised learning, it is called clustering. Okay, you do not have label. In regression, you use a continuous value as a label. In classification, you have a categorical data level. Okay. As of now, regression is currently the one of the very popular and handy tool for doing most of the predictive analysis uh, in the market research. Okay. Now I will try to quickly wind up the discussion on machine learning. So, what are some of the perspectives and issues in machine learning? So, to summarize, machine learning actually involves searching a very large space of possible hypotheses. Okay, what is the hypothesis? Hypothesis is a statement about some parameter of one or more population. Okay, so since we are handling big data sets, so machine learning involves searching this big data set to look for a possible hypothesis. Okay, and the idea is to generate one possible hypothesis, determine one that best fits the data that we are observing. Okay, so you have a training sample, and from the training sample, you generate a hypothesis. The idea is to have a hypothesis that best fits this observed data. Okay, so some examples of algorithms where we use to search the hypothesis space are linear functions, logical descriptors, decision trees, artificial neural networks, etc. Okay, then these different hypothesis representations, they are good enough for learning different kinds of target functions. Okay, so target functions in the sense, what are the kind of labels that you would like to have your algorithm learn. For example, it is not always yes and no, but it can be true. But it can be, for example, in Gmail, you have your personal, promotional, and so on. So these are my target functions. And then if you have to, let's say, separate out uh, fruits, so you have apple, orange, etc. These are my class labels. The target function can keep changing from application to application. Okay. So the best idea is that think think learning as a search problem. Think learning as a search problem while considering these points. Size of hypothesis space to be searched. This defines the volume of data that one needs to handle. Number of training examples that you have. So training examples are not always sufficient in many of the GIS applications. For example, if the area if the area belongs to a place which is not easily reachable, maybe in a valley or in a very distant location, then probably your training samples would be very less. Often the lesser training examples can bring can create imbalanced classification problem. So then it has to be treated in a different way. So it might happen that out of two classes, class A may have 80% of training samples, whereas class B may have only 20%. Okay, definitely class A will have more dominant presence in the training samples, and the training sample will be in some sense skewed, creating a imbalance problem, right? And then the confidence that a hypothesis is consistent with the training data, okay, and we'll also try to generalize the unseen examples that we have not seen while learning. Okay, so typically designing a machine learning problem will involve a number of design choices, selecting training experience, a target function that you want to the algorithm to learn, okay, and then finally an algorithm for learning that target function. Okay, so this is a very simple problem. Okay, you have a pattern, you need to predict what will be the next one, right? This is a typical prediction problem. Right. We know from our rules in our mind that what could be the next item that will come out. Okay, this example, so you have certain patterns drawn, okay, and we believe that this represents class 1, this represents class 2, right? So what about this? So this is a typical classification problem. Okay, so we learn from the training samples of class 1 and class 2, and then try to decide what will be the class label for this particular input. So this is a typical classification problem. Now we extend the classification problem. We learn with varieties of data, with lot of variance in the data. Okay, for example, we learn with so many different types of cars and so many different types of aeroplanes, and then to try to predict what is, then try to classify what is this car or which is this flight or plane. Okay, so the essence of learning says that there has to be a pattern. Okay, pattern may not be captured in a mathematical expression, and we should have data on that. We should have data on that, on it. Okay, now let us see this particular slide. So here we have a function trying to represent the top row. Okay, we have a function trying to represent the bottom row. What about this? What about this? How do we derive a function for this particular symbol? Right. So to continue the essence of learning, we have seen that there has to be a pattern, which is already evident in the previous example. Pattern may not be always easy to capture using a mathematical expression, and we should have data on the pattern and seeking a process that can capture the underlying pattern without we needing to explicitly spell it out. It's called learning from data, and that is what we have been doing in the previous one-time examples. We learn from data, then we predict, or then we classify. Okay, so from the data we derive features. So let's say, for example, we have class 1, class 2. We define features as, in this example, number of black boxes. Okay, and then we have a graph showing training samples, a number of black boxes, and from this we try to see what are the features, and then based on the features we derive some rules. For example, if 1 then class 2, if 2 then class 1, and so on. So essentially from the data we derive features, and most of the machine learning algorithms, they work on these features. Okay, so learning involves searching through a space of possible hypotheses, okay, to find the one that best fits the available training example and other constraints that you impose on the problem. Okay, so to summarize the overall ML experiment, you have a learning algorithm. We train it with various training features, training labels, develop a model. Okay, then we input features and then predict the labels. Okay, once your labels are predicted on the test case, then we evaluate the algorithm with some accuracy measures. So we do not have more time to discuss various accuracy measures, but you are welcome to look into some of the standard textbooks, which will definitely highlight what are the essential accuracy measures that people use in various machine learning tasks. These are some very important issues that most of us will face once we start working on the machine learning problem. Which algorithm performs best? Okay, so given that you have so many algorithms, which algorithms you think will perform best? Which algorithm will you pick up? Okay, or which type of problem and representation, and what are the parameter settings that we will use? These are very much experimental. One has to keep on doing until they find optimal set of parameter settings for a given learning algorithm and data set. How much training data is sufficient? This is rather difficult to say at this point of time, but will depend on what kind of problem settings you have, how much data can be collected beforehand, and so on. Okay, when and how can prior knowledge guide the process of determining correct target concepts? Okay, so if you have prior knowledge, how to bring that prior knowledge into the problem domain? Okay, and how can the learner automatically alter its representation to improve the ability to represent and learn the target function? So if you change the target function, how will a learner automatically change its representation so that it improves in every stage to meet as close as possible to the desired target function? Okay, now we will slowly move to an example. So I have some examples of image classification. Okay, image classification, all of you may have already done it many times. It is a kind of a procedure where you assign class label to every pixel in the image. An image is made up of pixels. Pixels are your picture elements, right? So in a classification, in classification, we try to group them or place them in classes or themes based on some quantitative information. These quantitative informations are come from your training samples and are matched to the gray level values of the image. Okay, and these quantitative information, they represent some characteristics. Right. So I will show you one example, and then we will go ahead and to formulate the problem from the same example. Okay, so we did some small study of the Bangalore city. Given that over a period of 20-25 years, the city there has been tremendous urban growth in the city, and because of that, large number of buildings have come up. So look at the change happening. Some kind of a spatio-temporal analysis was done. Okay, so this one here, what you see here is the as of now the boundary of Bangalore, Greater Bangalore, which happened to be Bangalore city earlier. But if you compare it to a false color composite, you see that the city has grown much beyond the Greater Bangalore boundary. So we have new areas, for example, the new airport here, Nilmangla town here, Electronic City here, and then Hoskote here, which are beyond the boundaries, right? So we took an area in the image which is bigger than the Greater Bangalore boundary, and would capture the recent new urban sprawl and growth that has happened. So the current example is to demonstrate the utility of classification task, classification in machine learning. What could be one potential use of classification? Right. So I have a 1973 image of Greater Bangalore area, actually much bigger, much beyond the Greater Bangalore area, and you see that that the urban areas are only concentrated in this part. Okay, the city was very small, and all over the remaining part was more of greenery and more of lakes, being shown in green and blue color. And the pink color represent others, that could be vacant land or open land, which are very less in that year. Okay, in 92 the city has expanded further, shown by the red pixels. In 2000, still further, 2004, 2009, 2014, 2018. Okay, I do not have the latest data on 2020, but you see the kind of the red pixels, the way it has grown in all directions, showing the spatio-temporal change in the city. Right. So image classification as such has numerous applications. One of the applications being shown currently in the form of a spatio-temporal growth of a city. Okay, visualization of this type of growth is not easy. Researchers have proposed large number of ideas to show what could be uh, different ways to capture, not only capture but to visualize. Right. So one possible way is the diffusion model, where you see where you show the changes happening in between each year in different colors. Okay, there could be there are many other possible ways of visualization of this kind of data, but visualization of these sprawls are still a challenge, and people go with discrete numbers and colors to show what changes have taken place. Okay, now these spatio-temporal studies, they not only show how a city has grown by the red pixels, but also their impact on other resources. For example, the water bodies have declined. Okay, the greenery has declined. So water body was declined by almost large percentage. Okay, uh, 3.2 percentage, and there was a 66 more than 66% decline in the amount of greenery as seen in the previous example. So they give us some kind of a current picture as what's decreasing, what's increasing, what could be the future change. Okay, now I will try to formulate the problem statement for the unmixing algorithm. So we saw that in the previous classification class. Okay, one pixel has been assigned a single class label. Okay, single class label either to buildings, urban, or to water, or to vegetation, or to open area. Right, urban, vegetation, water, open area. Now here what happens, we assume that each class is mutually exclusive. Therefore, if one pixel is assigned a class, the same pixel may not hold the same class. Right. But in the actual practice, this doesn't happen. Okay, and often pixels of lower resolution, they tend to have mixing of two classes. Okay, as an example, you see here that you have a pixel, and there are two smaller objects within the pixel. Okay, along with the background. So you have actually three different classes within a pixel. Okay, in the second example, you see again that you have three boundaries of three different classes merging within a pixel. Okay, or in this example, you see that the road which is a linear feature, is passing through the center of the pixel. So all these cases, they form a case where there are more than one classes, and these classes make up the mixed pixel problem. Right. So till now, what we had seen in the previous example, that we were assigning this whole pixel to one class, maybe urban, or maybe water. Okay, maybe water, or maybe vegetation, and so on. Right. But what we see here is that it's not only one class, but 1, 2, and 3 classes being merged. Right. So in some sense, if you have, let's say, a 30 meter by 30 meter pixel, and if it is let's say having three classes, water, and urban, and some kind of settlement, vegetation, and water. Okay, settlement being shown by red color, water being shown by blue color, and the remaining white background, let's say vegetation. Okay, now if you look at this particular row, the second row, okay, shows 20% of the area is settlement, 60% is greenery, and 20% is water. In a normal classification, what happens is whatever is the dominant category, for example, dominant category is vegetation, entire pixel is assigned vegetation class. This is called per pixel classification. Whereas in subpixel classification, we tend to estimate what is the proportion of settlement, proportion of vegetation, proportion of water within a single pixel. Okay, within a single pixel. So now we are trying to move from per pixel classification to sub-pixel classification and try to estimate proportion of settlement, vegetation, water in a single pixel. Okay, so traditionally this technique was proposed in 1992. Okay, where a simple linear model was proposed to solve the problem. So as you can see, we have one pixel here. Okay, it has three classes, 1, 2, 3, and the three classes form a mixture. Right? So this simple linear model was used to estimate what would be the proportion of the three classes. So let's say this single pixel has some reflectance, which we denote it by small y. Okay, so the reflectance, how do we formulate the problem is as follows. The reflectance of this pixel, which may be some number, let's say for 8 bit uh, data, it could be from 0 to 255. So any reflectance, maybe let's say 60, right? So reflectance, let us denote it by y, location x comma y, okay, of this pixel equal to summation of the product of area reflectance of class 1 into area of class 1, reflectance of class 2 into area of class 2, reflectance of class 3 into area of class 3, plus some random noise eta, right? So alpha n here, this is a scalar value, and in some sense it represents the functional coverage of n member 1, 2, and 3 at this particular pixel location, which has the reflectance as E1, E2, E3.
I also don't know.
So this is popularly called a linear unmixing model, and there are two constraints imposed. Okay, two constraints imposed on the problem. The first constraint is called non-negativity constraint. Other is called sum to one constraint. Okay, non-negativity constraint says that proportions of any of these classes cannot be negative. Sum to one constraint says that if you add up all the proportions, it should be equal to 1 or 100%. Okay, so the first solution proposed by was using using ordinary least squares. Okay, ordinary least squares. Just 1 second. Okay. The first proposal, the first solution proposed to this problem was using ordinary least square. Okay, and in ordinary least square, y is the reflectance. Sorry. Y is the reflectance of the pixel, and E is the reflectance of every class present in that pixel. Alpha is the abundance. If you take a norm and then solve it, so we see that alpha is equal to E transpose E inverse into E transpose y minus lambda by 2 into 1, where lambda is given by this expression. It's the solution. Alpha will give you the proportion of every class in the pixel. Okay, recently in not recently but 2 decades back, a professor from University of Maryland in electrical engineering department proposed another solution called OSP, which is called orthogonal subspace projection. So there he treats reflectance of a signal as as a desired signal, and reflectance of other non-target materials to be undesired signal. Right? He says that we can use signal processing algorithms to solve this problem by treating object of interest as desired signal and the background reflectance of other objects as noise. And he proposes a DU model. So D is desired, U is undesired, signal, and then plus with some random noise eta, and then by maximizing the signal to noise ratio, he is able to come up with a nice equation alpha p, which can help us to determine the proportion of individual classes in a single pixel. Okay, so now at this point of time, many other methods have also been proposed, and I will show you some in at the later part of the talk. Okay, so this typically assumes that you have your you have your so you have your this is your ground feature. The sunlight hits the earth, and then it is reflected back to the satellite sensor, right? And we are trying, our focus is to look at this particular object of interest, right? You have a sun here, and sunlight hits and comes hits the object, and the reflected energy goes back to the sensor. Okay, the problem in real world becomes more complex when the sunlight not only hits the object but is multiple scattered before it reaches the sensor. It can hit a tree, it can hit a tall building, it can hit an aeroplane, and then go back to the sensor. So this kind of problem is perceived as non-linear mixing. Okay, so we have attempted to solve both linear unmixing and non-linear unmixing, and try to see what could be the effect in the solution if you assume the problem both as linear and as non-linear. Okay, so the non-linear mixture model paper was published in the Information Journal, and we tried to attempt to solve it using um, using a neural network technique. So I will skip some part of this. This is the architecture of the multi-layer perceptron, where we try to see whether we could solve the problem assuming it to be a non-linear mixture of different target classes. So we use a logistic regression here. Now I will show you some of the results. Before proceeding into the actual real-world data, we generated a computer simulated data set of 200 bands um, by taking libraries from the libraries of 4 different minerals: alunite, woodugite, kaolinite, and calcite from jet propulsion laboratory. As using this particular expression, we simulated 200 bands, out of which you see band 1, band 100, and band 200 here. Okay, and this is an output of a simple machine learning classification, where every class, every pixel is assigned to one of the 4 classes. Now here you see the output of linear mixture model. Okay, so this is my actual classified output which I had shown here. Okay, and these are the B, C, D, and E are the 4 outputs of the 4 different minerals, showing their abundance. So abundance ranges from 0 to 1. 0 means complete absence, 1 means complete presence. Okay, any other value between 0 and 1 represents the fractional proportion of that class in that pixel. Okay, so if a pixel has some value of 1 in E, the remaining the value for the same pixel in remaining maps will be 0, 0, 0, and there will be as many abundance maps as the number of members. So the term classes in supervised classification are referred to as members here in this problem. And this is the output from the non-linear mixture model, which was solved using the neural network architecture. And you can see here the 4 different graphs of linear mixture model and non-linear mixture model. Amount of deviation you can is not clearly visible. So it happens that non-linear mixture model proves to be better in trying to estimate the proportion of classes within the pixel. Okay. The experiment was conducted on different resolutions of data. Okay, and we see that these are the outputs for 2 class: vegetation, non-vegetation, and 3 class: urban, vegetation, and non-vegetation. So these are 2 different lakes in Bangalore city. Okay, and this is, I think, Madiwala Lake at the bottom, and the one here is Alsu Lake. So the Alsu Lake is brighter in the pixels, so the value is close to 1. So in the remaining two images of urban and vegetation, the value of that pixel will be 0, indicated by black color. Okay. Now, the same technique was applied on real-world data set of an area closer to the international airport called Chikballapur district. Okay. Earlier, Chikballapur happened to be a part of Kolar district, but now it's separate. And then we had 6 classes: delta, forest, plantation, wasteland, water body, and the dominant was the agriculture crops. So this is the abundance map for agriculture. You see that most of the agriculture area are shown as white pixels. Okay, and then the settlement here settlement here is being shown here in the second abundance map. Okay, this is the Nandi Hill forest, which is shown as here in the classified image. This is your plantation, and this represents the wasteland. So you see that quite a dominant area is wasteland, which is being shown as pink in this image. Okay, and the last one indicates the water bodies, which shows that the district has very less smaller lakes or ponds, and there is no perennial river in the district. Therefore, the district is actually very arid with very scanty rainfall and is mostly dry. So we analyzed the amount and magnitude of error that happened in each of these classes, and amount x and y is the location, and the error magnitude is shown on the z-axis. Okay, so we found that some of the errors were concentrated in this part of the area. The reason is that this agriculture land had no crops, and therefore it was a fallow land which got mixed with the open area or wasteland, creating confusion between agriculture area and the wasteland area, and that was the major part of the error in the whole procedure. Okay. Then the various metrics were used to see how far is the output from both the linear mixture model and non-linear mixture model. Relation coefficient, RMAC, etc. were used. And all the experiments, they showed that definitely non-linear mixture models are proved to be better compared to linear mixture model while testing across different resolutions, different pixel sizes. Although non-linear mixture model is difficult to implement and very tricky if you are using some kind of a network like neural network or those kind of techniques. Therefore, a non-linear mixture model has not gained that much popularity because of its slower learning rate, because of the complexity in trying to understand the proportions for different classes, etc. It can also happen that there are variations within the classes. For example, when I say buildings, buildings can have terrace made up of cement, made up of asbestos, made up of tiled roofs, and so on. So when I say buildings, it actually means all types of buildings, whether it is cement, concrete, tiled roofs, or asbestos, and so on. But how do you actually capture this variability among the different types of materials used for the building construction of, for example, the terrace? One of the work where we did was to look at the n member variability within the mixed pixels, and we came up with some proposed some of us one of a solution to solve this use and called it a VECLS algorithm, variable end member constraint least square solution. And we try to use this method to take into account variability of different classes within a class. For example, vegetation is one class, but the reflectance of different species of trees, for example, small grasses, big mango tree or a banyan tree, rice field could be different, right? So within the vegetation or within the forest area, what are the variations of different species in that area were accounted with limited number of ground samples and classes, and there are some results which shows how the things change when you actually change the resolution and look at the variability, and how does that output change when you have too much variability in the class, medium variability, and low variability within the classes. So we compared this algorithm with one standard constraint least square method through different indexes for 2 class, 3 class, 4 class problem, and showed that the proposed method actually takes into account variations within the classes and estimates better proportion for all of these classes. Okay, now having seen smaller studies on unmixing on a single area or a smaller area, we move to big data sets and then try to see how could these algorithms perform when we handle bigger data sets. Okay, so we all know that now people have moved away from gigabytes to terabytes, and not terabytes to petabytes to exabytes, zettabytes, yottabytes. So current climatic data, they currently are stored in several petabytes, and that often goes into exabytes. But in future, we can anticipate that the current climatic data for the entire globe may well go into several zettabytes to yottabytes. Right. So in this particular study, we wanted to look at some of the advanced algorithms that are also used in solving the mixing problem. And it happened that apart from the statistical model, the linear mixture model, and the OSP, what we had seen earlier, lot of advancements have taken place in sparse regression, single subspace projection, geometrical methods, and lot of new statistical methods have also been proposed. So the challenge is to find out the technique or optimize the technique that can scale not only from a single scene to many scenes, but can scale on a larger data sets, which are computationally efficient, are more accurate, and also the ones that are robust to noise. So we did some preliminary study to compare these algorithms and then check out which is the more robust technique. So we found that the technique that we had used earlier, the least square solution, was one of the stable versions, and we had typically used the unconstrained least square method and then imposed two different constraints. We came up with an unconstrained least square solution and then imposed two constraints, the sum to one constraints and non-negativity constraints. Now, later in the year 2001, Professor Chang again, he came up with, he did several experiments and then found that if you put a constraint on this solution and make it a constrained least square solution, the output of that technique seems to be more efficient. So we borrowed the code from him and ran it on a single scene, and actually observed that it takes a very long time, maybe 2 hours for one scene. Okay, it was a MATLAB code, so we converted it to C++ code, but the time again required for one scene was very high. So, so the challenge here was that we saw the entire procedure, and we found that um, imposing the two constraints simultaneously is not that easy on this solution, and because of that, algorithm becomes very slow. Actually, most of the current literatures proposing different solutions on this problem, they are restricted to very smaller scenes of 200 pixels, 200 rows by 200 columns, and therefore are able to show nice outputs. But if you want to scale up to one scene or to at a country or a national level or a global level, the algorithms actually either fails or it performs very badly on such larger data sets. So we found that imposing the two constraints simultaneously, not in a sequential manner, but simultaneously, is a hindrance that is making the algorithm very slower. So we refer to one of the books by Lawson and Hansen, least square problem, okay, and try to take up the technique where they show how to impose the two constraints simultaneously using non-negative least square. Okay, so the algorithm fully constant least square, they extend the non-negative least square, which was adopted from Lawson and Hansen, and we reworked on the algorithm to make it more faster. Okay, and then once we did that, we found that the execution time came down to 2 minutes per scene from 2 hours per scene, and then verified that algorithm using different comparison, different unmixing techniques. So the classes what we took here were limited to three: substrate, vegetation, and dark objects. Substrate refers to soil, sediment, rocks, and non-photosynthetic vegetation. Vegetation refers to green photosynthetic plants, and dark objects represent clear water, deep shadows, absorptive substrate material such as soil, which has water content in that, right, which has absorbed water. So these three end members were derived by Professor Small, and they had published this work in multi-scale standardized spectral mixture model, remote sensing of environment, and they have already placed all the reflectance of the three classes on their website here. We took the reflectance of these classes for Landsat data and started our experiments with that. The reason why we did this is because we wanted to handle global level data sets where classes could be actually infinite, right? And that would lead to a lot of problem while doing validation. We wanted to have some kind of a representation of the so many infinite classes into a limited number of countable classes. And this paper gave us a nice starting point to go ahead with the classification task. So globally, 100 different places around the world were sampled with Landsat data. Okay, and a graph was plotted for three different classes: substrate, vegetation, and dark objects. And the average of these mean of these end member reflectance for the three classes were considered to generate the end member matrix. Okay, then we did one small study first with the simulated data where we kept on increasing the signal to noise ratio from 0 to 2 to 4, 8, 16, 32, 64, 128 to 56, and looked at the performance of the algorithm with increasing noise variance, and then subsequently two different experiments, one in an urbanized area in San Francisco City, which has a mixture of buildings, roads, and greenery, and another area which belongs to agriculture farm in Central California. That is, the place is called Fresno, where we had physically visited and collected training samples. Okay, so the training samples you can see are marked by uh, black black rectangles and black squares in different part of the scenes. So we had collected training samples for each of these fields. Okay, and initially tested the algorithm on these two different data sets. Okay, then once we were happy, with the results, satisfied with the results on the two different landscape, then we moved on to look at some of the global data sets and to handle 8,003 scenes for the global data a year and for a month, and then we had 10 years of monthly data for the entire globe. So each scene in this data has approximately 5,295 rows and 5,295 columns, which make up 224 billion pixels.
Okay. Shall we have some questions? There are actually many questions.
Yeah, I'm about to finish in another 5 minutes, and then 10 minutes we'll have it for questions. Okay, so some of these validation metrics were used to look at the efficiency of the algorithms: RMSE, signal to reconstruction error, probability of success, error matrix, and so on. And these are some of the graphical results which show the performance of different unmixing techniques over different data sets, simulated as well as real-time data set. And then uh, the actual algorithm was merged with random forest classifier, okay, to make the abundance output, to convert the abundance output into discrete classes, because abundance output was rather difficult to validate for larger areas. So we had put a threshold and used a random forest classifier to convert the abundance output to discrete classes. In the four discrete classes were urban, forest, farmland, and water bodies. Okay, supercomputing environment was used with 29 petabytes of RAID disk storage, and then this is the global data set which I had talked about with 8,003 scenes for 2011, and these are the outputs for the same data set for your three different classes: substrate, vegetation, and dark objects. We see that the portion in substrate is very close to the NDVI. for NGVI of the same area, which also represents greenery. So it proved that the signature taken for the vegetation area was good enough to to extract all the greenery pixels from the entire global data sets. For the single state, accuracy were computed for 4 different classes: forest, plantation, water bodies, and urban areas, and were compared with some of the standard data sets. So these, for example, this figure represents both farmland, forest patch, and water body. Here you see extraction of water body by the algorithm what we proposed, and this is a San Luis reservoir with some canals. So you see that in these two outputs the canals are lost. Canals often get mixed with highways, and therefore they are classified either as highways, or highways get classified as canals. So it is actually difficult in a normal classification, whereas in unmixing it was easy to extract those pixels which make up the canals. And then for the urban areas, two big cities, San Francisco and Los Angeles, were considered. We integrated the urban areas with nighttime data set, which shows the amount of light emitted in the night time. And we integrated the nighttime data with the urban areas, believing that these lights they come out from the buildings, so they are part of urban area, and extracted the urban areas for the two cities here, and matched it with standard machine learning technique to see how far unmixing is uh, comparable or better than the normal machine learning techniques. So validation was done across 100 different sites across the state, and the sources of errors were analyzed while trying to compare the output with different standard outputs. Okay, and we found that there was 6% improvement over random forest technique, and while comparing the output to standard published map by the government. Okay, in another work, we have used a semi-automated probabilistic framework to actually classify every single tree in a 1 meter NAPE data. Okay, and this particular paper was published in IEEE Transactions. And now I will try to quickly wind up by listing some of the challenges and research opportunities in this area. So one of the greater challenges that all of us spend a lot of time dealing with our own data, because people are not willingly ready to share the data. So we keep on arranging our own data, downloading our own data, and spend the majority of time. That actually leads to a lot of redundant storage of the same data set, takes away a lot of processing facilities, and in some sense they result in larger overall computing budgets. Moving data sets are getting uh, that are getting larger every year is actually also expensive, given that it takes a lot of bandwidth and time. And still people have actually moved ahead, and they are now sharing their codes, results, workflows, but still there are limitations to that. So that lead us to do the same work again and again, and codes and workflows, if they are shared either through published paper or through GitHub, etc., that would actually facilitate us to go beyond the current research and do something different from whatever has already been done. So what are the needs? So visualization of spatio-temporal data is still a challenging area. Trying to handle big data sets in terms of volume access is still a area that people are working on. Development of scalable processing and advanced spatial analytics tool are still areas of research. Developing robust machine learning techniques that can well take care of complexity, noise. Also work in limited training samples is still a new area. People are working on that. Handling multi-resolution, multi-temporal data is difficult. People are working on that. Deep learning is a new area people are trying to explore in geospatial data analysis, and also promotion of and use of free and open source softwares, making the data public, making the code public is now the requirement of the time, so that more and more people get engaged to these kind of technologies. Okay, having seen this, recent trends in machine learning areas are trying to look at classification, object detection, segmentation using deep learning techniques. CNN, faster CNN, Yellow, or SegNet, PSPNet, or the algorithm by Facebook, which is called FAIR, have been recently being used in lot of papers, and lot of papers are also being published in different domains, such as wildfire, precision farming is another great area using UAV datasets, deforestation, spatio-temporal data, SAR data, all using one of the recent deep learning techniques are currently the recent trends. So I acknowledge all my supervisors, and I would like to end my talk here. And thank you all of you for attending and listening to me patiently. I welcome any questions from your side.
Participants, any questions from your side? Okay, or we will first read those questions. We have a question from Dr. K. Rao. Sir, how prediction is used for weather forecasting using satellite data?
So as I explained earlier, in prediction we do more of a interpolation. So prediction techniques like linear regression, for example, they guarantee interpolation, but not always extrapolation. So there are time series models. Like for example, it's a completely separate course by itself, looking at time series data, such as for example moving average or ARIMA, etc., and so on. So those are dedicated to handling data sets where you want to predict something for the future. Okay, but so the two terms, prediction and forecasting, are different. Given that prediction is widely used in a data, or trying to look for a data which is missing from a time series data set. So whereas forecasting would be something like you are trying to predict uh, any parameter, for example, for 2021 or 2022, or try to look at the urban growth in 2025. So these are examples related to forecasting, whereas prediction will be something like you want to retrieve certain data sets or parameters for the year 2012, which by mistake, because of manual error or because of electronic error, was not recorded, but you have data sets for other years. So we can use some kind of a regression technique to predict the missing values. Actually, prediction as such is also, linear regression as such is also used in a lot of data pre-processing techniques, such as for example, trying to fill up the missing value imputation. So people use global mean, some people use nearest neighbor, and very often linear regression is also used to not only linear but also non-linear regression is also used to predict such values that have been missing either due to data capture or due to some other error. Whereas forecasting might it relates to time series data, where we use time series models. One can actually go through some of these models online, or there are very good books which I can um, share with you. Okay, which talks about how to handle time series data and then do forecasting.
Okay, sir, thank you. Now,
Mhm.
the next question is from Ashish Paul. How machine learning will help in estimating carbon sequestration in plantations?
Okay, so machine learning can definitely be adopted to such problems. Although I have not got a chance to work on this kind of specific domain, but given a chance, given if you are ready to explain me certain basic ideas as to how do you estimate carbon sequestration, what are the parameters involved, what are the variables involved, definitely I can try to see how it can be done. So apart from what I'm saying, there will be definitely papers on this where people have been using. I have actually seen some papers, not yet read them, just downloaded and left it in my laptop. But I have seen that people have been using machine learning to estimate carbon sequestration. I don't know what are the variables they consider, what are the observations they have, and what type of data they are actually handling. But given a chance, given to with those data sets, definitely we can work and we can see how do we model such data sets to, I mean, predict carbon sequestration.
Thank you, sir. And the next question is from Nayama.
Mhm.
If we want to extract any particular feature from an image, the shadow of available in the image affects the thresholding and feature extraction of an image. Is there any way to reduce the shadow effect?
There are actually shadow gates merged with all the darker objects in the image, such as, for example, if there is a deep water, deep water, or a soil area that has absorbed a lot of water. So these classes, they tend to get mixed together. So there are a few ready-made index which people have, researchers have proposed. You can try using such index to see if they can be used to extract shadows and separate it from other classes if such confusing classes occur in the same image. Okay, but one can also try to incorporate some background knowledge or ground information if you have, and if you know that how in which part of the image you can separate out the shadow from other similar looking objects. So the algorithm at first iteration may not be able to separate these two classes and maybe show them as one class, but with use of some shadow index and also with the use of some prior information as to where are the shadows in the image, we can definitely try to mitigate the effect of this class merging in the image.
Okay, sir. Our next question is from Nagaratnam. Can we use the machine learning algorithms for satellite image fusion? What types of algorithm is best for fusing
Yes.
panchromatic
Yeah.
and multispectral image?
Yeah. So currently, I have come across a few papers, specifically from the deep learning domain, where people have tried deep learning to fuse multispectral and panchromatic data, multispectral and SAR data. So although I have not gone through the details of how the architecture works, what kind of subsampling, resampling they have done, sampling or upsampling they have done, but I have seen some papers trying to merge the spatial and spectral properties of different data sets to have improved resolution. So probably the recent advances in deep learning techniques. They have they have been exploited. They have been used. You will get actually good number of papers on data fusion using deep learning.
Okay, sir. The next question is from Farsana Shaheen. How machine learning will help in mineral detection?
So machine learning has been, I mean, well used for object detection. Mineral detection is a problem which, in a broader sense, narrows down to object detection, where mineral is an object, right? And there have been numerous techniques people have used for decades to solve such problems, given that you have the signature. So mineral detection is currently more limited towards hyperspectral data than multispectral data, and there are a lot of detection algorithms, especially currently state-of-the-art object detection techniques like your YOLO or RCNN, okay, with VGG16 as a backbone. They are currently being used, the Facebook detection algorithm. So you might have seen in a Facebook, I have not logged in very often, but I have seen earlier when you log in, okay, Facebook automatically recognizes your friend's face and highlights it in a box and shows that this could be possibly one of your friend you can connect to, right? All these fair algorithms from Facebook, they are being used for object detection, also in face recognition. Um, uh, so, uh, there are large number of papers, large number of techniques available for mineral mapping using hyperspectral data or high spatial resolution multispectral data. So some of these data sets are free. For example, the Nevada data sets, you just Google Nevada hyperspectral data. You will get both the data set as well as the spectral signature of some selected minerals. Okay, you can download the signatures as well as the hyperspectral data and perform this operation on your own before you get the data for your study area. So there are 2 to 3 data sets: Indian pines and Nevada, and two are very popular, where you can download not only hyperspectral data but also the corresponding mineral signatures of different minerals in the form of a spectral library. And large number of papers are there to help you to see how to apply these machine learning techniques to extract those minerals. Hope this would give us some answer to go ahead with the look for Nevada data sets and look for Indian pines. These are two popular hyperspectral data in public domain, which are being used widely for a lot of experiments.
Thank you, sir. Now, next question is from Eskosh. How machine learning will be useful for urban landscape configuration and urban growth prediction?
So I had shown you one very small case study of the Bangalore city. So this was a very rudimentary study, but I would say that probably the number of papers on urban sprawl is too high. I mean, one cannot even read. So you will get thousands of papers on trying to look at urban sprawl of a city in different journals using time series data, and all of them about different machine learning techniques being applied on satellite images to classify them. They use some kind of spatio-temporal model. Some of them use spatial indexes. For example, trying to look at the centrality metrics, or actually the term is spatial metrics. They use spatial metrics, centrality metrics, irrigation metrics, and so on. So they help us to configure. They help us to take into account the amount of sprawl that has taken place that you can make out from the classified scenes. So please Google some of these keywords: urban sprawl, multispectral, future growth, urban growth, etc. And you will get lots of interesting models. Okay, and moreover, the data sets is already free, so you can incorporate that and maybe test it for your particular case study.
Okay, sir. The next question is from Debashish Chakravarti. What do you mean by size of hypothesis? How size is computed in machine learning?
Okay. We actually didn't talk about size of hypothesis, but I was referring to the space that you have look for the hypothesis. Okay, so I don't know, maybe I would have spelled it wrongly, but what I actually wanted to mean is that you have a very large data sets, such as for example any big data, and then from the data you are trying to formulate a hypothesis. So you look for the so the challenge here is that how do you actually come up with a hypothesis to be proved or disproved using any machine learning algorithm, okay, from that larger data sets, because it's difficult and challenging to handle large data sets with so many variables, so many attributes. So which variable do you account for in your model? Which variable you can afford to neglect because it's not significant is a challenge. And therefore, keeping in view all these independent variables that you are considering in classification, the hypothesis space becomes too large. So now the challenge is, how do you formulate a hypothesis that takes into account the significant variables in your data set? Okay, and then using that hypothesis, how do you conclude or come to a nice conclusion by either proving that or disproving that using the data set?
Okay, next question is from Sarida PS. When you talk about linearly separable and non-linearly separable, how you do data separation on the basis of accuracy versus precision parameter? How is morality kept in check for such a professional profile? How do you rectify the erroneous data to incorporate in the study?
Okay, we'll try to answer one by one. If I'm not able to answer, you please mail me, and I will again think on the possible answers and then reply you back. So your first question says, when you talk about linearly separable and non-linearly separable, how would you do data separation on the basis of accuracy versus precision parameters? Right. So accuracy. So when you talk about accuracy, so for a two-class separation, two-class problem, you have two by two contingency matrix. That is a true positive, true negative, false positive, false negative. Right. Now from this contingency table, or also the called the pattern matrix, confusion matrix, you then derive precision, recall, and sensitivity, specificity of a metric, right, of a data set. So now, non-linearly separable data is difficult, really difficult to handle. So, the best way I have attempted is that we go to the ground. I'm talking about the spatial data. We go to the ground and using some kind of a tape, long tape, and a GPS, which is pre-calibrated. Okay, and we select a we select an area of a known, we select a field of a known area. Let's say if my data resolution is 250 meter, for example, okay. So I go ahead and take up a patch on the ground, which is at least 300 meters or 300 meters by 300 meters or slightly bigger, given that there will be some mistakes, errors in correcting the data, I mean image. So if I have a data set of 250 meter by 250 meter resolution, okay, so we go to the field with a GPS, we note down the four corners of the field, okay, and then if there are multiple crops, for example, in the field, we try to measure approximately how many meters in terms of meter square area does a particular crop exist in that field. So we collect some similar data sets for other crops in the same field, okay, and we try to have a complete description of that field. Likewise, we shift to some other area and also gather some more data from other fields. That could be mixture of different crops or mixture of houses and crops, so on. We note down what are the attribute information and then use this data for validation. I have seen people also using Google Earth image or any high resolution image. So you zoom in as much as possible. Google Earth is actually difficult because you do not know what is the resolution at the reverse end. But with a panchromatic image, where you know that resolution could be 1 meter, 60 centimeter, and so on, you can actually identify objects and delineate them by drawing polygons. Okay, and then combine all these polygons and you get an idea of what is the composition of different classes in a single pixel. We use these data sets to validate our output. So we try to see that what best can be done from our side in terms of data collection. Obviously, errors will be there. So to get an idea of the algorithm's performance, it is better to start your study with a synthetic data, simulated data, where you have the option to control the amount or proportion of different classes in a given pixel. Okay, and because it's a controlled experiment, you exactly know what is the proportion of class ABC, and then you run your algorithm, get the output, and then you compare the proportion, estimated proportion from the observed proportion, and then see how close they match. If your algorithm performs good in a synthetic data, you are then ready to it forward on a real-time data, on a real-world data. With the real-world data, definitely you have to put effort, go out, spend a day, take a lot of ground information. At least the whatever data you collect should be good enough to validate. Okay, and then based on that data, we have to uh, look at the accuracy measures. So if there are multiple classes, for example, not only two but 5 to 6 classes, then computing accuracy becomes slightly trickier. but we try to maintain it to the best of our practice, keeping in view whatever we have seen on the ground. Okay, so the errors can definitely be reduced once you have seen, once you know what are the points of error and what could be the possible sources of error. One can add